Good afternoon once again. So I will talk about MUTAFRAME. This is a data visualization platform for predicting the effects of mutations. Before I jump into the whole process, I will briefly talk about the team. So we started this project like a year ago. We completed it a couple of months ago, and then the whole process took about 5 months. So you can think of the whole process, you can split it in half. There is the predictor part, and then there is the application part. For the predictor part, currently MUTAFRAME harbors a single machine learning-based algorithm. For those of you who are interested in machine learning, it's a random forest-based algorithm. It's an aggregate predictor, and it's trained using the Humor dataset. Mainly, Daniele is working on this machine learning. He's the author of this algorithm, and also he's working together with Andrea Gazzo and Gabriele Orlando. So this right half, I call it the Italian block. So, and then on the left half, there is Julien. He's responsible for the server side maintenance, also the database, and for the front end, I'm responsible for the entire framework and also the data visualization tools. We have 2 PIs for this project. So there is, at one side, there is Marianne Roman. She is more interested in the structure, 3D structure of the proteins. So we are, currently we do not harbor this feature yet, but we are planning to extend MUTAFRAME to have support for 3D structure. And at the other hand side, we have Wim Ranken, who is more interested in the sequence of the proteins. So before I jump into my part of the story, I will just briefly touch barely on the surface of the information flow between medicine and bioinformatics. Now, if you think about the relationship between the patient and the doctor, the first thing the doctor does is to what I call delineate the phenotype. So he tries to get as much information as possible regarding the patient's phenotype. So by this, he does it via MRI data. He uses the tissue samples, blood samples, and then the next part is to combine this with the genotype part of the story. And the desired expectation is that it leads to a diagnosis, but usually it doesn't. The reason is that this is a needle in a haystack problem, because what about the polygenic context? So now, even now, we are starting to think that at one point we thought purely monogenic diseases, certain traits can be, let's say, influenced by some other variant in another part of the genome. At the other hand side, we have the overlapping phenotypes. How do you really distinguish between two similar phenotypes? Also, the number of possible targets, no matter how much you filter down your candidate gene list in your VCF file, you always end up with 20 or 30 targets, which is no good if you want to do functional studies. And also, what is known and what is not known in literature is also part of the problem. So for me, what is the gold standard? There is no crystal clear answer for that. So for me, therefore, prediction, additional tools for prediction for reducing the amount of candidate genes is still a good way to make effective use of the resources that we have for functional studies. So there you go, MUTAFRAME is a prediction algorithm. It's a platform for data visualization. And by referring to mutation, I'm referring to strictly single nucleotide variants. I know there's a whole world out there with deletions, insertions. We really want to expand towards that direction, but currently we are really concerned with the single nucleotide variants. So this is about the tech stack a little bit. I'm going to speak for the machine learning-based aggregate predictor, as I talked. Its name is Deogan2. It is written mainly in Python. For the backend, we have some scheduled maintenance loops and scripts written in C, and then the database we use MySQL, and for client to server communication we use PHP. And on my side, I'm just using JavaScript ES5, and then it's in 2 parts. The first part is a collection of micro libraries which I call Lexicon. These are data visualization tools written in JavaScript ES5 and D3, and then the rest is consists of the framework itself, which I call the view and the controller layer of a typical MVC framework. So if those of you who are interested into the algorithm, the machine learning algorithm, you can take a look at it, the paper that we have recently published. Well, I mean, recently in 12th of May 2017 in Nick Lakes' research. So those of you who are more keen on learning about random forest and how it is coupled with the web app, you can just read the paper. Now, in my part of the story, the first question I had to ask myself was, who's going to use this tool? Yeah? At one point, I can say there's going to be a researcher aspect. They are more interested into the underlying data. Okay, you get a score, and then what? How this score is generated. And then also a detailed breakdown of that score. So I have a mutation on my protein, but what about the other mutations on that protein? And at the other hand side, we have the story of the medical doctor. From my experience, they are really fond of tools that are easy to use. Of course, they are not used to the terms in bioinformatics like the researchers, so a bit of explanations in your web app can also help. And at the same time, if they can get a couple of figures for their case studies, they become really happy. So this is the layout of the application, so maybe I can just show it over here. All right, so normally it starts with just your sequence, you define your sequence, and then it gives some general information about your mutated and wild-type amino acids. You have some dashboard over here which can break down the chemical differences between, you have the overall score here, and if you want to see which features are contributing to it, you can see it as well. Over here you have the machine learning contributions, you have the raw scores of where those real values coming from, calculated from. You have the distribution of your mutation. So here is your mutation, for instance, but what about the rest of the thousands of possible mutations? And then also you have a heat map representation of the same mutation. And a couple other features which I will just skip over for brevity. Okay. So my problem was, we have several different data types, so I need to make small macro libraries that is suited for each data set. So we have the lexicon plot, which is for two-dimensional data. We have the lexicon SS, which is for secondary structure. We have the lexicon simplex, which is it's just a simple bar chart with an ordinal scale on the x-axis. We have the lexicon distribute, it's for distribution. Lexicon compare for comparing two plots. We have a lexicon rainbow. This is kind of strange, I don't know where to put it. It's just like a mixture of a bar chart and a minimal Sankey. And then we have lexicon sec, which is to visualize protein sequence. Lastly, I have the lexicon dash, which generates simple dashboards. Now, they all share a common pattern, so if you want to use it in your own web app, in your own visualization, you just instantiate one of the objects from its constructor, and then you use the common methods to specify the width and height, and then there are some component-specific methods. You specify your input, and then lastly you call the append over here, the append method, to initialize the internal variables, and then you call the render function to render your first scene. For those of you who are working with JavaScript and D3, can I see how many people are working with D3? Oh, yes, nice. Normally, maybe you're not used to it, but when you are working in JavaScript is prototype-based language. So basically, you would expect that there is some methods in the prototype chain. But in this case, each object is strictly private. So there is no method search in the prototype chain. There's a reason why I chose that. I can explain it if I have time after the presentation. But for the brevity, I will just pass this. Now, this is the first module. This is the Lexicon Stick module. This is basically just your protein sequences. You just drag and drop your FASTA file, and you're able to just visualize your sequence. Now, this uses semantic zoom, meaning that every time you do a drag gesture or click a button, it's re-rendering the entire scene. These are SVG elements, so it uses the canonical D3's enter, update, and exit pattern. And there's also a programmatic control, meaning that external software or another function can control where this tool is going to be, where this tool is going to show, and stuff like that. So it means you can still use the REST style queries. Now, this is the canonical way to provide input. So I think this way is much easier for medical doctors to use, but you can still use the RESTful query. So I said about semantic and geometric zoom. In the advantages, well, the disadvantage of semantic zoom is you are all the time doing DOM manipulation. That's not a good thing, because these objects are very expensive to add and remove from the tree. But at the same time, what you're gaining in spite of performance is the layout control. And also, you don't forget that in semantic zoom, you can actually mimic the geometric zoom. In geometric zoom, you render it once, you distort it many times, either in x-axis, y-axis, or both. The transitions will be smoother. So on the bottom, you have the same tool. I just pass in one method on the right-hand side, so it can mimic the geometric zoom. This is also a timeline graph from Google Chrome. So the performance comparison between visualization of 500 and 500,000 sequence length. So two FASTA files here. There is minimal burden in scripting because basically when you are rendering the scene, you're working on small data chunks. The moment you drag and drop your FASTA file, it's chopped up in small chunks, and whatever transformation you're doing it's on those small pieces of data. So this allows it to impact minimally on the performance. This is the second module. The Lexicon Dash basically is just a simple bar with, on the left-hand side, you have 0 benign to 100% deleterious. You have an overall score, but then if you click on it, you get a distribution and the feature contribution of different features. So in the case of MUTAFRAME, in Deogen 2, we have several features which Deogen relies on. So you can see how much each feature contributed to the overall score. This Simplex is also a scatter plot bar chart organized ordinally on the x-axis. So as a developer, you get the control. They share the common y-axis, but their range, meaningful range, can be different. In each range, there's a gradient showing the red part, the deleterious, and the blue benign. And when you mouse over, you get an idea about the score's value and its interpretation. And I think it is quite important for the medical doctors as well. So this one is Lexicon Distribute. This shows you a plot of your entire possible set of mutations in your protein. So you can actively change the bin size. In this case, it's based on you, so you can make the intervals larger or smaller, and when you mouse over the bin, you get how many values are inside, what is the interval of that bin, and so on. One nice feature is that based on your bin size, again, you can get the area under curve. So if you have your mutation, you locate your mutation and you want to see how significant is that, you can quickly look at it, change the bin size, get a new distribution, and redo it. So of course, there's also one more button which allows you to decompose the bin into its individual data points. So this way, one graph is composed of, in average, 10,000, 15,000 points. So you can mouse over them to get idea about the data, the score, the index in your data set, and their label. So you can control how the zooming is changed. So there is over here the X, Y, and axes, so you can independently zoom. There's a map to give you a sense of where you are, because it can really get crowded, and you get information about individual mutations. Next, you also have a tool, a brush tool, which allows you to go along your data set and see which points are there in your distribution. So since this data set is sorted based on the residue count in your protein, you can ask strange questions like, which part of my protein has the most amount of mutations with the highest score? So that allows you to see functional regions in your protein. Of course, just by passing in a few methods and just transforming the data, you can use the same tool, the same data, to show it in a very different way. Now on the left-hand side, you have the distribution. On the right-hand side, you have a heat map with 20 possible amino acids and that position, and then the residue count on the x-axis. But it's exactly the same data. So you have this region over here, which is color-coded. You can pass, as a developer, any function you want. Now the blue is benign, red is more deleterious. You have this entire region here, which is enriched in mutations that are have higher score. So if you actually move on to the same region in both distributions, then you get more or less the same result. So this is just the same way of looking, different ways of looking at the same data. This is the lexicon plot. This is, I have done this for another predictor actually, which we were planning to incorporate into MUTAFRAME, but we did not. In this plot, you have the overall view of your entire data set. This is the position along the protein, and then for every amino acid, you have a value. Now, based on the amino acid or your data type, you can change these, change the bin size, the histogram type, or based on chemical property, you can color them. So the way to do this is, since I'm using semantic rendering here, individual elements, I was planning to write a library to string interpolate the SVG path data, but I think there is no need at all. So in my case, I just need a couple of polygons and some smooth shapes. So only you need is 6 points. All you do is to transition the position of those 6 points. And in case you need a smooth shape like a circle, so how do you go from a hexagon to a circle? Basically, you just also transition the radius from a sufficiently large value to the desired value. Basically, a sufficiently large radius is a radius that is a couple of times larger than your viewport width or your height. And these are not lines, these are just arcs. So when you transition the radius, you get the effect of smooth transitions. This is just one way of a zillion ways of doing the same thing. But if your own projects, you can also use a similar approach. This is Lexicon Compare, so you pass in 2 plots, and then it generates a comparison between the 2 plots. So you have the common axis over here, which is the position along the protein, and now you have the y-axis of the first plot, y-axis of the second plot, and you have pairwise cross sections over here. The good thing about it is that these tools can be synchronized with each other. Just by using simple modules, you can really construct complex visualization. So when you, for example, zoom out or zoom in or move one of these tools, and the box adjusts to its changes position. And when you mouse over any of these points, then you also get a sense of where you are in the other data set. And recently, I get my hands on, maybe a month ago or so, this data set about amino acids. These are a collection of a very large text file of a collection of hydrophobicity index, or, for example, signal sequence helical potential index for amino acids. Think of these as 20 by 1 tables. It's like 20 amino acids and 1 score for each, but many of these tables, thousands of these tables. And I had this idea, if I have an ordinal scale at the top and then a linear scale at the bottom, so the first table will be at the top and the second table will be in linear scale at the bottom, I can really compare these 2 tables from the drop down over there and then the drop down below. So it really gives you a sense to compare these 2 tables quickly, fairly easily. So also I use this data set in a larger, more general, the same tool in a general data set. I got my hands on the 2016 voting results in the United States. So this way you can look at the voting values from Clinton, from state to state. You can do the same thing to Trump. You can go down and you can sort them based on your criteria in your JSON structure. You can look at the individual states, and so it's just what you're doing is you're dissecting the JSON and you're creating views out of it. So I want to apply this to the protein sequence, so because not only you can show absolute scores, but also you can show spatial data. So what I'm after is not only economy of motion in DOM manipulation, but also economy of motion in JSON structure. And why not use all of these components all at once? Because half of the tools I manage, I talked about, I'm not using it in MUTAFRAME yet. And because it takes really time to understand your tool and its limitations. What sort of data does it work with best? It looks like a trivial question, but it's really not easy to answer. So few things that works for me as a closing. If you're working with the canonical enter, update, and exit pattern in D3, it's much better if you're not going to use this. If you're just going to render each scene, just go very low level in JavaScript and create your own DOM element generators. It makes it much faster, much painless. At the same time, if you're going to, even you're dealing with DOM rendering, so even if you're not dealing with WebGL and you're not dealing with Canvas, you're just using SVG elements and you have a render function, you can just use request animation frame to throttle the calls to your function to make it really smooth. And this is an example from a pure SVG 3D renderer I have written a couple of years ago. Using the request animation frame makes it much faster. And lastly, just experiment. I do not think there is something called absolute truth, so just experiment and see what works best for you. Thank you very much.
So I have, I can give 1 minute maybe for a question. Somebody thinking of a question for you? So that was sort of a mixture of, you know, a new way of thinking of this way of visualization. But in the beginning, you mentioned that the really big importance is the interface with the application, like the medical doctor or the biologist. I wondered if you had tested this with a medical doctor.
So right now, at the moment, in the main website, we just have, for instance, this is not even, so if you, it's just a simple heat map, and if you want to really break it down into simple mutations, you can do that. Medical doctors usually use right over here. They just want to use these features, just to mouse over these, some of these values. So that's it. And then researchers are more interested in the bottom part, and medical doctors are more interested in the top part. So.
Okay, fair enough. So thanks again, and let's move on.